Welcome back to our AI cat seeing cat tutorial. In the previous video, which is not necessary for you to watch, by the way, because of its craziness, I showed how I came about the calculations for the movement of the eye pupil. In this video, I'm just going to go ahead and just write the code, and then I'll try to explain um, if there's anywhere. If you remember the code, let's go to form1.cs first. Okay, if you remember, we said we wrote this just for us to test the draw pupil at method of the eye class. So now that we know it's actually working perfectly, what we actually want is, we don't want to draw the pupil at the position of the mouse. However, what we want is, we want the eye to look at the position of the mouse. Okay, then also we'll do the same for the right eye, and we'll just go ahead and remove that. Remember, we said that was for testing also, so I'm removing that, and I'll go down here and do the same for the right eye. So we want the right eye to look at picture mouse position GFX. Okay, so this is what we want. So at the moment, if you remember, we haven't actually coded the LookAt method. So now our form class as it is right now, it's complete, because we've handled everything that we need to handle in the form class. All that we need to do now is, we need to set up the LookAt method. That is where the main calculation for drawing the pupil is. So let's go to the eye class and code. As you can see, there's nothing in the method for now. But before we actually write that method, there's a helper method. Remember, I said I would have preferred to use the vector class, but because of the we're using the point f class, there's a method a helper method I would like to create, which is for getting the magnitude of a vector. So I'm going to call that private float. Is going to be a float magnitude, get magnitude, or call it get magnitude with a capital M, by the way. Get magnitude, and or maybe call it get vector magnitude, and you just pass it a vector. Okay, since we're using points, obviously we're going to pass it a point. So we're going to say p, or we could use a point, and inside there, what you want to do is, you want to return. Remember how you get the magnitude of a vector is x squared plus square root of x squared plus y squared. So what we need to do is, we need to return math dot square root of x squared, that's a point dot x times a point dot x plus. Okay, so I'm just going to wrap that inside brackets, and then do a summation of a point dot y times a point dot y. So I'm taking the x component of the vector, multiplying it by itself, and then adding it to y component of the vector multiplied by itself, and then find the square root and return it. So Okay, the reason why it's complaining is because we need to cast it to a float. Okay, let's do that. Let's put a float because as it is now, it's a double. So I'll need to cast that to a float. Okay, I think I know why that's giving us issues. We want to cast the total, that's everything after we've finished the computation. That is when we want to cast it to a float. Okay, so this is the helper method, get vector magnitude. We'll use this to get the magnitude of a vector. Next, we're going to go ahead and write our LookAt method. If you haven't and you really want to know how we came about the calculation, I suggest you look at the video where anyway, it's not a very clear video, but at least you get an idea of how we did it. For the LookAt class, I'll just go ahead and write it and then explain it later. Point P equals new point. So this P is going to be the resulting vector. That's the vector of the mouse position minus minus the eyeball center. Okay, so it's going to be a point. So we've passed the mouse position in and we called it a point here. Okay, so a point dot x minus eyeball center dot x. So that's how usually, if it was a vector, we could have just done a point minus eyeball center, but because it's we're using point f, we'll have to do the calculations by ourselves. Okay, so it's going to be the y component is a point dot y minus eyeball center dot y. Okay, so that's p. We've gotten p. Next, we need to get theta. Theta is equal to, by the way, if you don't know what, like I said, I mentioned all this, the p, the theta, normalized p. There are so many parameters that I used in the previous video, so in case you're wondering what all these are, they are from the previous video. Theta is equal to, I'll need to cast the results, whatever I'm calculating here, to float, math dot arctan, so that's the tan inverse of p dot y divided by p dot x. Okay, so that's our theta. Now I would like to mention here that whenever you use this arctan or tan or sine or cosine, any of the trigonometric functions, you should always be careful because like sine, cosine, tan, they take radians. Okay, the angles they take are supposed to be in radians, not in what do you call it, not in degrees. Okay, so you realize in this code when I'm writing, I don't even bother converting them to degrees or converting it back to radians. The reason is because you see why I don't bother, because look, I'm doing a math.arctan of this, which means it's going to give me a result in the angle I'm going to get is going to be this theta I'm going to get directly here is going to be in radians. Okay, so that's why when I take this theta and use it in my next calculation of finding sine or cosine or tangent, I don't really bother about changing it to degrees or radians, because I already know the theta is in radians. Okay, so if in case you're doing other calculations that involve trigonometric functions, you have to make sure you keep track of whether you're putting your angles in degrees or in radians. Okay. All right. So after that, we'll say point F, normalized P is equal to new point, new point F actually, new point F. Then we provide the x component. If you remember, is cosine theta. So it's math dot cos theta, math dot cos theta. That's the x component, and the y component is math dot sine, actually, math dot sine theta. Okay, and by the way, we need to convert these to floats. Okay, we need to convert this to also float because they are actually double. When you the math dot cosine and math dot sine return double. Okay, so you have to cast it to float. Okay, so that's our normalized p vector. We've gotten the normalized p vector. The next thing we want to do is compute r. So r r is a vector. So point f r is equal to new point f actually r is not a vector. If you remember in the video when I was doing, I said r is the distance or the magnitude of the target vector we're trying to get, such that we do not exceed outside the boundaries of the eyeball. Okay, so r is a float. Okay, so float r is equal to I'm going to say get vector magnitude of p. Okay, so it's like saying p dot magnitude. Okay, since p is a vector, remember this our get vector magnitude helper method that we created. So the magnitude of p divided by now remember in the calculation we said we were going to use maximum r, and we said maximum r is the width, half the width of our what do you call it, of our form. That's the enlarged form. So for now, I think basically you can use just about anything here, but what you should know is that if you give it higher than half the width of the form, that's the resolution of your screen, your the pupils of the eye are going to be they're going to be coming outside of the radius of the eyeball. Okay, so that's why we said the maximum should be that. So I think I can use something like, I think I tried 400 f. And by the way, if it's too small also, it's going to be as if the pupils are not really moving at all. Okay, the movement is going to be, so the smaller this value is, the smaller the motion of the pupils, and the larger it is, the higher the motion. So the best value is actually half the width. Based on our calculation, the best value is half the width of the of your screen. That's the resolution of your screen. Okay, so anyway, I think I tried 400 in the previous when I wrote the program. I used 400 and I think it worked fine. So we can always change it if it's not good enough. So I'll use 400 for now, 400 f, and then we multiply this by the eyeball radius. So eyeball, remember we're in the eye class now, so we just call eyeball radius. Okay, and let's not forget our semicolon. Okay, so the magnitude of vector divided by this multiplied by, yes, perfect. Next, we're going to calculate our look vector. Now, I'll explain what the look vector is. Point F, look vector is equal to, no, not that, not like that, not look. Look vector is equal to new point F normalized P dot x. Remember, we've calculated our normalized P dot x, our normalized P. So normalized P dot x, comma, normalized P dot y. Normalized P dot dot y. By the way, we will need to multiply this by r. Remember, we've computed our r here, so we know what r is, and then we use, this is like r cos theta. If you remember, normalized P dot x is cos theta and normalized P dot y is sine theta. So it's just, instead of recalculating again, we can just use the already calculated result and do that. Okay, dot y times r. Okay, and finally, I think that's the look vector. So by the way, the look vector is just the vector that starts from the center of the eye to where the position of where the eyeball is going to be drawn. Okay, that's the vector. Okay, so it's not from 0, 0 to, remember when we're doing our drawing, like when we're calling draw pupil at, we're supposed to give it OP, that's O to actually the look vector, that's the terminating point of the look vector. But hereby the look vector is actually from the look vector here that we calculated is from the eyeball center, okay, to the point where the draw pupil at is going to be drawn. So that means that we're going to need a final position here. That's the final position of the pupil. We're going to call it final position is equal to draw pupil at, oh, sorry, not draw pupil at. I'm beginning to get tired. I think it's way past my bedtime. Okay, final position is supposed to be equal to new point F eyeball center dot x, exactly. So we're going to take it, like we're going to take the center of the eyeball and then add this vector. It's just like saying eyeball center, sorry, not eyeball radius, eyeball center plus, that's this vector is eyeball center plus the look vector. Okay, eyeball center dot x plus look vector dot x, that's the x component, and then the y component is eyeball center dot y plus look vector dot y. Okay, now I have done this. There are some things I actually missed out in this code based on the calculation, though in the calculation we did in the previous video. That's a crazy video. These were all the things we only considered. Okay, we didn't really consider some things. I just want to show you what it's going to look like if you try to run it. There's actually a bug here and it's not so easy to find, okay, because it probably took me like I think a whole day to find out what was actually wrong with this particular code that we've just written. But for now, let's just run it and see what it looks like. Okay, so finally we're going to say draw pupil at final position, and we pass it the GFX. Remember, the GFX is already passed from the form 1. Okay, so we do that, we save, and finally voila, we can test. Fingers crossed. Okay, exactly. You can see the problem we're having. So already, yeah, you can see. Okay, let's start with this. First of all, you can see that the 400 that we provided for the for the width of the actually it's not even that. It's actually, I think it has to do with the eyeball radius that we use. I think the eyeball radius that we use is probably too big. Okay, I think we use 33. Yeah, no, 33 pixels should be fine. I think is the is the 400 that we use in the width. I think it's way too much. Now, anyway, if you look at the way, if it's on the right hand side, it's working. It looks like it's working correctly. Okay, I think the first thing we do is let's just rectify and make sure it doesn't go outside the boundaries of the eyes. Okay, let's go back there and say instead of 400, let's divide it by say 800 actually. So we divide the magnitude by 800 and multiply by eyeball radius. Okay, so let's go to let's test it now and see. Okay, it's a little bit better. As you can see, it's still going outside the eyeball, but at least it's not much, so we can still increase that 800 to let's say 1,000, or yeah, let's try 1,000. So let's test that. Okay, we're just about getting it right. Okay, I think we should increase from 1,000, let's say 1,200. And I believe, yes, finally. I think I still don't like the way it's popping out like that. So I'll do 1,300. Okay. I still don't like it. Sorry about that. I'll just add 100. So 14. Okay. Yeah, I think I can manage this. I think it's okay. Okay. So now if you look at it on the right hand side, when the mouse is on the right hand side, it's working correctly, working perfectly fine. But the moment, notice this right eye, the moment the mouse is to the left of the right eye, or to the right of the left eye, see what happens? The right eye is working correctly, but look at the left eye. If I go down, it's going back up, it's going up, and if I go up, it's going down, right? So which means it's actually working correctly when the mouse is to the right of the eye. Now look at it. If the mouse is now on the left of this left eye, notice what happens. They both do not work correctly, and it actually took me a very long time to find that bug actually, and it has to do with the way I think it had to do with the way theta was being calculated. Okay, if you look at theta, okay, I might have to, for me to show you the real problem, I would have to pull out my notes again, which I really, after what happened in the previous video, I really don't want to do that. But I'll try to explain. Let me just put in the code and I will explain what's going on. Okay, so it has to do with actually the quadrants. If you remember your uh, 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 what do you call it, if you remember your trigonometric functions, okay, depending on the quadrant, that's if it's on the right quadrant, if it's on the top right quadrant, or the top left quadrant, or the bottom left quadrant, or the bottom right quadrant, there are some oddities or some odd things. Like we were even taught, I remember in maths, we were taught something like cast, where they say if it's on the I think top right quadrant, all the angles are positive, or all the trigonometric functions are positive. It is on the top left. Only the sign is positive, something like that. I'll try to explain what that how we're going to. It has to do with that anyway. So I'll go ahead and write what I had to do to correct that. So first, I had to come up with a polarity variable, which is also a point. It's supposed to be a float, but because it also has a x component and y component, so I'll call it a pointf. Okay, so I'll call it polarity is equal to new point f 1 comma 1. Okay, so if you notice from the program, in fact, let me run it again. If it's on the right hand side, notice what happens. If I go up, the eyeballs go up. If I go down, the eyeballs go down. But look what happens if I'm on this side. If I go up, okay, by the way, if I'm on this side, if I go left, it's going to the right, which is wrong. Okay, it's supposed to follow me to the left also, which means it's kind of inverted, right? Also, if I go up, the y goes down, and if I go down, the y goes up. That's the pupil. The y component of the pupil goes up, which has to do with the polarity. We need to invert that, but you can't just invert it anyhow. You'll have to sit down and find the correct way to do it. So this is the correct way to do it. You put an if p dot x is less than 0, and so this p now is our vector. When you do eyeball center, a point, that's the mouse position minus eyeball center. Okay, that's your p. So if that resulting vector, the x component, is less than 0 and the y component of that vector is also less than 0, what you will have is polarity dot x is equal to -1, and polarity dot y is equal to -1. So you invert the polarity. Okay, then also you're also going to test. Now this test is when, let me just go back to the design view. That test we did is when, notice your quadrant, imagine there's a straight line that goes down from the top and goes vertically down right in between the two eyes. That goes down right from the top in between the like it divides this eye into two. Okay, and then there's another line that goes across like that, that divides that eye into two. Now the top right quadrant is this quadrant. Okay, at the moment our calculations are correct when your point is somewhere within this quadrant or somewhere within this quadrant. That's the top right quadrant and the bottom right quadrant. But when your point is in the top left quadrant and it's in the bottom left quadrant, it's wrong. Now what we just did, that if condition we just put, is for solving the problem for when the point is that the mouse pointer is in around this area. Now remember, the quadrants are different for each eye object. Okay, I'm doing it based on this eye. So for example, this point, when this mouse pointer is here, it is actually on the top right quadrant for this eye. However, it is on the top left quadrant for this eye. Okay, so in the in this if statement, what we are testing for, if you can see, if p dot I is p dot x is less than 0 and p dot y is less than 0, we are actually testing for when it is on the top left quadrant for that particular eye. Okay, so this happens, and then if we'll have to also do if p dot x is less than 0 and p dot y is greater than 0. Okay, that's for the bottom left quadrant. Okay, remember, like I said, the Cartesian for the Cartesian system for the for Visual Studio, for the graph we're using now, it goes from top left. Okay, it runs from top left, so y is going downwards. So the bottom left quadrant means y is actually positive. Okay, so if that occurs, you will need to do polarity dot x is equal to -1. You have to invert the polarity, and polarity dot y is equal to -1. Okay, is that right? I was thinking we'll only invert one. Oh, okay, I think that's right. Then finally, remember, we've added a new control mechanism called polarity, but we haven't included it in our actual calculation. So this is where you will actually use it. You'll use it at the end where you get the final position. So the final position is equal to the look vector dot x and this eyeball center dot x plus look vector dot x. However, you multiply the look vector dot x multiplied by the polarity dot x. Okay, and then the same thing for the look vector dot y. You will have to multiply it, so you will flip it for when it is in the top left quadrant and in the bottom left quadrant, top left quadrant and in the bottom left quadrant. You need to flip the polarity. That's the direction of the vector. Okay, so look vector dot y times polarity dot y. By the way, I've only written the code and I've explained a bit. However, believe me when I say, to find this bug, it wasn't just trying to see what's wrong. I had to go down into actually calculating the cosine and everything. Like, it's almost like deducing the whole formula from start for you to be able to find this little quirk. And like I said, it actually had to do with the way cosine works. You see, cosine of a negative number, if you remember, our theta is the tan inverse of y over x. Okay, and then when you come to do cosine of like, you want to get x, you need to do cos theta. You have to do r cos theta. Okay, now the cosine of a negative number is actually a positive number. Okay, and then let me see if I can remember. And the sine of a negative number is a negative number. The tan of a negative number is also a negative number. However, for the cosine, it behaves weirdly in that the cosine of a negative number gives you a positive number. Okay, now anyway, That's part of the reason why those this kind of quirkiness comes into play. And also with the fact, combined with the fact that when your x is on the left hand side, that's when your x is negative and your y is negative. When you do y over x, what you end up with is a positive number. Okay, so that's some of the issues that causes that problem. Anyway, enough talk. Let's just test this and see if it works. Yes, it works. Yes, it works. Okay. Um, it was a very long video, but I hope you guys enjoyed it. If you do, hit a like, and I'll try to come up with an even better program for this, because I have an idea of another program we could actually create. However, it's not going to take much time like we did here, because we're going to reuse the I class that we used, and most of the things that we've already written, we're just going to reuse that code. Okay. All right, I'll just go ahead and play with this a little while before I close it down. By the way, I like this the size of this pupil. It's kind of correct in that in the previous one I did, the pupil size was very small. Okay, thank you for following.